we haven't gotten the data. And my point is that the politics of the day should not sabotage science. They have the data. They should share it with scientists. They can wait with any press release. But for the scientists to analyze the data, that would serve an important purpose of helping us design the future observations of this object. I should also say that the news yesterday was that this object came closest to the sun. And it received a huge amount of heat from the sun. Mm-hmm. And the latest report indicates that it became extremely bright, much more than expected for familiar comets.
What does that tell you?
Well, that is not the most unusual fact. It actually is bluer than the sun. And a blue color usually indicates very high temperatures if the light is emitted by some hot surface. But the sun is 5,800 degrees Kelvin above absolute zero, and it's very difficult to keep a surface hotter than that. In fact, an object at the distance of 3I Atlas from the sun could only be 20 times cooler than the sun, so it should be redder. And any dust.
But so what does that mean, Avi? What does that mean if it's hotter than the sun?
We have another anomaly. The object is bluer than the sun, which we don't fully understand. And as of a few hours ago, the first hint for a non-gravitational acceleration, meaning something is affecting its trajectory beyond gravity, was indicated. And so what I'm telling you is that there are new facts about this object that make it even more interesting than it was before.
3I Atlas has astonished scientists once again with the strange behavior observed around its perihelion. Its unusual acceleration patterns and unexpected blue coloration have drawn significant attention, and the situation has become even more controversial due to NASA's delay in releasing key high-resolution images, a delay officially attributed to the U.S. government shutdown that began on 1 October 2025. The result has been growing concern in the scientific community over lost time-sensitive data and questions about transparency. Astrophysicist Avi Loeb has pointed to several critical observations that heighten the mystery. On 2 October, the high-rise camera aboard the Mars Reconnaissance Orbiter captured images of 3I Atlas from a valuable sideways perspective as it passed within 30 million kilometers of Mars, a view that could clarify the geometry of its mass loss and surrounding glow. Yet these images remain unreleased. Meanwhile, data from the Atacama Large Millimeter Array on 29 October showed the comet deviated by about 4 arcseconds from the trajectory predicted by gravity alone, suggesting additional forces or processes at work. Taken together, these findings underscore how much remains unknown and why the withheld observations are now at the center of intense scientific interest. This is not the first time an interstellar object has challenged conventional expectations. The first known visitor from beyond the solar system, 1I Oumuamua, in 2017, also displayed a non-gravitational acceleration without the typical signs of cometary outgassing. Its behavior sparked ongoing debate about the physical mechanisms that could produce such motion. With 3I Atlas now showing similarly puzzling acceleration near perihelion, researchers are faced with a second data point that forces reconsideration of what interstellar comets may be, how they form, and what material properties allow such unexpected dynamics. The details surrounding the mass loss behavior of 3I Atlas are particularly important. Prior observations suggested that evaporation and dust shedding were occurring, but not at a rate sufficient to explain the measurable deviation in its trajectory. The ALMA-based detection of a 4 arcsecond offset implies either a significant and sudden release of mass during a narrow window of time, or the influence of a driving force that is not yet fully characterized by standard comet models. Determining which scenario is accurate requires analyzing the high-resolution high-rise images and complementary datasets, information that would allow researchers to estimate the nucleus size, evaluate the structure of any surrounding dust envelope, and clarify the distribution of ejected material. Because of this, the request for data release is a scientific issue rather than a speculative one. Without access to the higher resolution images and full observational record, researchers are limited in their ability to model the object's composition, evolutionary history, and trajectory. The longer this uncertainty persists, the more difficult it becomes to reconstruct events that occurred in their perihelion, especially given how rapidly interstellar visitors fade and disperse. As 3I Atlas continues moving away from the inner solar system, the window to understand it is closing. For many astronomers, the priority is clear: release the data, analyze it collaboratively, and use this rare opportunity to improve our understanding of objects originating beyond our own star. Given this urgency, Avi Loeb has argued that the withheld data is not just a matter of procedural delay, it is central to addressing the physical mechanisms behind 3I Atlas's behavior. Loeb has pointed out that one of the most striking unresolved features is the object's non-gravitational acceleration, which cannot yet be fully explained without the detailed imaging NASA has not released. He emphasized that in the absence of those high-resolution observations, researchers are forced to rely on indirect measurements and incomplete modeling. Based on the trajectory deviations observed so far, Loeb has proposed that the acceleration could, in principle, be driven by an internal energy source rather than standard cometary outgassing. The non-gravitational acceleration might be the technological signature of an internal engine, he suggested, framing the idea not as a conclusion, but as a hypothesis that must be tested with the very data that remains unavailable. While the acceleration was one such anomaly, the color of the comet soon emerged as an additional point of interest. Most comets develop a reddish tint when heated, as dust and volatile gases scatter sunlight differently at close solar distances. However, 3I Atlas shifted to a markedly blue hue as it neared the Sun, a deviation that Loeb referred to as the 9th Anomaly. Blue emission in astronomical objects is typically associated with either very high temperature gas or specific ionized compounds, and both possibilities remain under investigation. Loeb noted that if the heating were internal, rather than merely solar-driven, the color shift might hint at a localized high-energy source, though he emphasized that confirming this would require spectroscopic analysis, data that observatories have only partially released. The comet's brightness also drew attention. On October 28th, amateur astronomer Vorachat Boonplod observed 3I Atlas brightening more rapidly than models predicted, with the comet reaching roughly magnitude 9 at perihelion. Bright enough to stand out against background stars, this rapid brightening suggested a large release of gas and dust, likely caused by intense thermal stress as the comet neared the Sun. However, as with the acceleration and color shift, the degree of brightening was stronger than expected for an object of its estimated composition and size. Loeb acknowledged that strong outgassing alone could explain the brightness, but also cautioned that if the outgassing were driven by internal heat, the phenomenon might not conform to typical comet behavior. The issue of unreleased observational data complicates attempts to resolve these questions. The high-rise images captured by the Mars Reconnaissance Orbiter represent the highest resolution views of 3I Atlas taken to date, with roughly 3 times the spatial detail of the best publicly available Hubble imagery. As noted earlier, these images were not released promptly due to the U.S. government shutdown that began on October 1, 2025. Loeb and other researchers argued that this delay has hindered the scientific response during a critical observational window. In Loeb's words, they should not suppress science. The concern is not political, it is practical. An interstellar object is a transient event, and opportunities to analyze its structure and evolution diminish rapidly as it recedes from the Sun. Meanwhile, observations from NASA's Stereo-A and ESA NASA's Solar Observatory recorded an extended glow around the comet near perihelion, broader and more diffuse than expected from ordinary sublimation. Portions of the dust appeared to flow not only away from the Sun, but also in patterns resembling an anti-tail, where material is distributed along the comet's orbital path rather than radiating outward. Anti-tails have been observed in some comets before, but the geometry observed around 3I Atlas appears to be more pronounced and irregular, suggesting a complex interplay of gas release, solar wind pressure, and possibly asymmetrical mass loss.
Another aspect drawing attention is the comet's trajectory through the solar system. Unlike most interstellar objects, which are expected to enter at highly inclined or random orientations relative to the ecliptic, 3I Atlas followed a path remarkably well aligned with the thin plane in which the planets orbit the Sun. Some orbital dynamicists have estimated that such alignment has roughly a 1 in 500 probability of occurring by chance for an object arriving from interstellar space. In other words, while not impossible, it is statistically unusual. This alignment is particularly noteworthy because the ecliptic plane represents the gravitational midline of the solar system, an area shaped by billions of years of planetary motion, migration, and resonance. For an object arriving from the deep galactic environment to enter this specific region requires either coincidence or some form of prior dynamical conditioning. This does not imply intentional steering or control, and the research community stresses this point carefully.
but the alignment does open important scientific questions about the object's origin environment. One possibility is that 3I Atlas was ejected from a planetary system structured similarly to our own, where large planets and a stable orbital plane influenced its departure. Another possibility is that the object underwent a sequence of gravitational interactions or scattering events during its interstellar journey, gradually nudging its path into a trajectory more closely aligned with the plane of the solar system. Alternatively, if 3I Atlas had been traveling through the galaxy for a very long time, its orbit could have been shaped by encounters with star-forming regions, molecular clouds, or unseen planetary bodies in the void between stars. Each of these scenarios carries different implications for both the age and history of the object, and each one requires more precise data to evaluate. Size and mass estimates further emphasize the significance of the object. Based on its brightness and outgassing properties, astronomers estimate that 3I Atlas could have a mass on the order of tens of billions of tons, potentially comparable in volume to an urban landmass such as Manhattan. While large comets exist, an interstellar object of this scale is noteworthy, particularly one exhibiting signs of energetic processes that may not fully align with standard comet behavior. If the mass loss observed near perihelion exceeded earlier evaporation estimates, it could mean that the nucleus of 3I Atlas is either more porous, more compositionally diverse, or more dynamically active than expected, each of which would carry scientific implications. As 3I Atlas moved beyond perihelion and began traveling outward once again, scientific attention shifted to follow-up observation campaigns. With the comet gradually emerging from the sun's glare, telescopes on Earth are regaining the ability to track it. Of particular interest are upcoming observations from the James Webb Space Telescope, which is equipped to capture infrared data that could reveal the molecular composition of the gas and dust around the comet. Infrared spectroscopy could determine whether the emissions result from common volatile materials such as carbon monoxide, methane, or water vapor, or whether less typical compounds or high-energy ionization states are present.
If the infrared signatures reveal unusual chemical ratios, mineral compositions, or temperature gradients, the findings could help determine whether the comet's behavior is consistent with known forms of volatile sublimation, dust fragmentation, or thermal stress expected in natural icy bodies. For example, JWST data could show whether 3I Atlas is releasing common compounds like water vapor, carbon monoxide, and methane at rates that match its observed brightness and mass loss. It could also reveal whether the gas emissions are isotropic, radiating evenly in all directions, or highly directional, which would have major implications for understanding its acceleration. If the emissions are uneven and concentrated in specific jets or vents on the surface, the acceleration might still be explained by natural processes. However, if the outgassing appears inconsistent with known thermal models, such as sustained energy output even when the object moves farther from the sun, this would point to a different kind of mechanism at work. At this stage, no conclusion has been reached regarding the ultimate nature of 3I Atlas. The object could be a natural product of an alien planetary system, perhaps shaped by conditions unlike those in our own. It could represent a transitional class of interstellar debris not yet cataloged in comet taxonomy. Or, as Loeb suggests is worth considering, it could be an artifact, a fragment, or even a remnant probe from a technological civilization. A possibility that remains speculative but scientifically testable as more data become available. What makes 3I Atlas scientifically valuable is not that it suggests one outcome over the other, but that it demands explanation. Interstellar objects provide rare insight into the environments of distant stars, the processes of planetary formation, and possibly the activities of technological species. Whether natural or engineered, 3I Atlas challenges researchers to refine observational methods, expand theoretical models, and prioritize transparent scientific collaboration. As new data arrive, especially from JWST and the release of the HiRISE images, the coming months may determine whether 3I Atlas settles into a known category or whether it forces the creation of a new one. For now, it serves as a reminder that the universe still holds phenomena that defy expectation, and that discovery begins not with certainty, but with paying attention to what does not fit.